Okay, so let's chit chat about the lab in terms of like big understanding as far as the test goes tomorrow. And by the way, yes, bring a ruler tomorrow, okay? Because you're gonna have to draw a diagram. Okay. All right. So on that first one, here is the basic idea: is that you had your light source here, and then you had some type of lens, and then you had the screen. Okay? So the whole idea was that you were going to calculate a theoretical value of where you could place the screen. So let's just talk about this. What's the only type of lens this could possibly work with? Concave or convex?
Convex.
Convex. Why?
Because it creates a real.
Well, if it was a concave lens, what would happen?
It makes it virtual.
It would get spread out. The only type of image you could form would be on the other side, which would be virtual. And so you could calculate it that you could only have one possible solution, and there would be no point in trying to project it onto the screen. Okay? So here's what I'm looking for in terms of your drawing. All right? There should be two of them on that back side. First off, okay, make sure that you label what's the object and what's the image and what's the focal point. I swear, in all my years of teaching optics, this class struggles more with labeling things than any other class I have ever taught. Okay? Seriously.
Is that a compliment?
No. The word struggle should have been an indication that it was not a compliment. Okay? Oh, mine? Okay? So,
they were asking what if we had to draw like a
settle down,
on the radar.
No, it's just a simple right there, and like we said.
yeah.
That's what we've been saying,
Come on,
right?
Shaq. You got Shaq.
Okay. So, anyway, so the idea being is if you come up with a theoretical value, you have your two magnifications. You know the drill, just sign it. You have your two magnifications. One magnification should be a fairly decent GPA, and the other magnification should be a horrible GPA. Okay?
Wait, on which one?
And both your magnifications should be negative values. Okay? So the negative value for the magnification indicates what?
It's upside down.
It's inverted. Okay? So on both of those, you should have seen an inverted image, which is going to be part of the next thing going forward. On your experimental error, remember that's your theoretical value minus your experimental divided by your theoretical times 100. Okay? So your projected values are what you calculated up above based upon theoretical values. Everybody's data is different. The only thing I can grade are those calculations. Show me both of the experimental error calculations. Okay? You're not just randomly writing down numbers and think I'm going to know what they're mean. Okay. It's really not that. Okay. So on the telescope part over on page 2. Don't. Okay. So here is the basic idea of what happened here. Is that you had your screen, you had the first, and on this one you've got placed the convex lens, right? At the 66 centimeter mark. Okay. So that's the first one. And then you've got a second one, and then you had the screen. Okay? So basically, if you go through the geometry, what happened is that here's your object. So the image of the first one became the object of the second one. Okay? That was the basic idea. So if you just have one convex lens, and here's the primary thing, if you just have one convex lens, what do you know about the image that you're going to make, upright or inverted? It's inverted, right? So in terms of a telescope, that's going to be a little bit awkward, okay? Mainly because of the fact that hey, let's look at the moon, whatever it is. And if what you're seeing is upside down, like, okay, well, that's awkward, okay? So there's that aspect of it. So the point being is that you're going to take that image and basically flip it up again so that you see an upright image, okay? So also, and this was on a relatively small scale, the other thing that you look at the telescope, what's the main purpose of any telescope?
To zoom in and get it bigger.
To get a magnification bigger than 1, okay? That's the whole point of a telescope, okay? And the bigger the mirrors are, or the bigger the lenses are, the bigger that magnification can be, okay? That's the whole point. So you use the lenses to do two things. Flip the image up and create a big magnification. That's the whole point. Now, there's a whole bunch of different types of telescopes. You can have ones that involve mirrors, ones that have pure lenses. Galileo was the first one to really use a telescope. This is why they're called the Galilean moons of Jupiter. And that was actually one of the things that they were able to use because of, if you look at where the Earth is, when it's on one side of the moon versus where the Earth is, where the moon is on one side of the moon, and the other side, they actually used that to get a very crude estimate of the speed of light. Because if Jupiter is over here, and here's the Earth, and here's the Sun, versus over here, then that distance to get to the Earth when it's on the other side, because they had a decent idea of what that radius was. And so if they knew how much longer it took for that light to get from one side, when the Earth is on this side, versus when the Earth was on the other side, and they knew what that time was, they were able to get a very crude estimate of the speed of light. It wasn't very good, but it wasn't bad. Okay, so obviously so let's talk about on the questions on problem number 1 with building the telescope. So obviously you can project it on the screen, so it is real. Okay, and this is talking about the image that you're projecting, that you ended up with projecting onto the screen. Okay. So obviously it's going to be upright. That's the whole point of this. So on that second question, some of you have some questions on that. So basically what I want you to see on this one, you have two convex lenses. So using 65 centimeters as your object distance. Now, let's talk about this in terms of the test tomorrow. What do you know about object distances? Are they ever negative values?
Never.
No. Okay. So you never have to worry about object distances being negative values. You can have SI that are negative. And you can have focal lengths that are negative, but your object distance are always positive values. So that first SI, okay, and this is what we're talking about, is that first set of lenses, okay? And what's in terms of what's going to happen. So that initial SI value should be around 30, okay? And that magnification should be a negative value, less than 1. And this, and whether it's upright or inverted, that's what I'm talking about. How'd that go for you? Didn't think so.
Hey, making sure gravity still working.
I'm sorry.
Gravity storm?
Yeah.
I hate it when that happens. And so what I'm asking, whether it's inverted or upright, I'm asking about that first image that is formed from the first lens. Okay? not the overall one. So the first one is inverted, but then it gets flipped over again, and then it ends up upright. Did that answer your question?
Yeah.
Okay. All right. So there's that. Any questions on that part of the lab? Good. Once, twice, sold. Okay. So let's talk about the second part. So this is kind of like the practical portion of the lab practice. So your focal length of the lens should be between 10 and 15 centimeters. And that magnification should be a horrible GPA. No, this is for this part. Oh. Yeah, this is for this. We moved on past the telescope. We're on to this portion. Okay. So the focal length should be between 10 and 15 centimeters, and the magnification should be a horrible GPA. Okay. Now, when you get to that question on C, Gavin had some questions on that side view. Now, here's what's weird about this one. This is what annoys me about this. I took this straight off the AP exam. So here's what's a little bit wonky about this one, and I was even frustrated when I saw this. They notice the arrow, Olivia Pruitt, okay, not a stick. Okay. So they had the object over here, and then the image. I know it annoyed me. It's like, no, it is not how everybody starts with the object on the left and the image on the left. That's just always how it's done. And it just annoyed me. It's like, God, who came up with this? Some British guy that wanted to do it wrong? Okay. Anyway, so it doesn't have to be exact. Here's the whole point of this, right? Is that with your calculations of part B, you show at least 2 rays. Ideally, you would show 3. Basically, all you have to do is show, hey, here's this thing. It's going to go through that focal point. It's going to go through the middle. You could do a third one where it goes through this focal point, something like that. Okay? As long as it's something close to that. Now, here's where you get into like the what if. Okay? Now we're going to submerge this in water. So it might be handy, if you want to reference, if you look on page 578 of your textbook. Okay? And I know I yelled this out at the end of the class yesterday. But if you look on page 578, it's a very up-close drawing of what happens when you actually go through, when it's refracted through like a lens. Okay? So we always draw it like it's one single refraction. In reality, it's actually 2 different ones. Let me draw this a little bit bigger. So you've got this action going on. So here's this curved lens. So it's going to come in here like this. Now, hopefully at this point, this should be old hat. So this is air. And this is something, let's say it's glass, whatever it is. Okay? All right? So, what's it going to do when it hits the glass? Slow down. So, this normal here is drawn relative to that curved surface. Okay? You all are used to having this being like flat. In reality, it's still the same idea. But when it hits that glass, what's it going to do? Going to slow down. So which direction is it going to get bent?
Down.
Downward. Okay? So it might go something like this. Okay? All right? Cool. Whatever that happens. Now, here's the story. Now, when it goes from the glass into the air, what's it going to do? Speed up. So then, which direction is it going to get bent further down? Or is it going to get bent up? Up a little bit. Okay, maybe something like this. Okay? Because when this hits, that's going to speed up and flatten that out a little bit. So there's actually 2 different ways this thing bends based upon that interaction. So here's the whole point of this question. Is that when you look at this in terms of how this is going to play out, it asks you what's going to happen when you put this thing in water. And this was actually, it's like, seldom do I look at the question and go, hey, that's a cool question in terms of, you know, wish I had come up with that. So here's the point. What if this, let's say glass is an index of refraction of 1.55, and remember, this thing is going to come out here and try and hit that focal point. So if this is 1.55 and air is 1.00, so if you remember back one of the very first demos that I did, I had that cooking oil, and I put the test tube in it, and it like disappeared. Okay, so down over here.
Still gone.
Go disappear. Okay, A for physics still works. So you can see it up here, but you really can't see it down there, right? Disappear. Why now that you know a little bit more about index of refraction, why does it disappear? Yeah, so the light can't tell the difference, right? It can tell the difference up here, but it can't tell the difference because the oil and the glass have the same index of refraction, okay? So the bigger the difference between the index of refraction and the other material, the more it gets bent. Okay, does that make sense? Right? The bigger the difference, the bigger the bend. The bigger the angle, if you want to think of it that way. So if I put this in a similar type medium, like let's say that the index of refraction of the glass and the liquid that I submerged it in were identical. Okay? They were identical. When this beam of light hit, what would it do? Nothing. What would it do? It would just go straight because there would be no difference in the indexes of refraction. Okay? So what allows you to have a focal length is that this thing is going to come down here like this and it's going to hit that focal point on the other side. Well, that's if there's a pretty big difference between the index of refraction that's in and the glass. So as you decrease the difference between those indexes of refraction, what's going to happen to the amount, to the angle that thing gets bent overall? It's going to become less. Okay? So when you get to that last question on part 2, says describe how the focal length and size of the image formed by the lens. Explain how the ray diagrams in part 2 supports your answer. So here's the deal. So when you look at that initial set of diagrams, okay, when you had this, okay, it's going to come in, boom, it's going to get bent, it's going to get bent. So then what I'm looking for is that when that lens is in water, do you show, sorry, I'm going to get a horrible cold. Some of you. I don't know who gave it to me. But then, what's going to happen is that when you put that in water, that angle is going to become smaller because there's this, the change in the value isn't as much. And so therefore, that focal length then is further out. Right? So on part 2, where it says, describe how the focal length of the lens changes, you just need to realize that that focal length is going to become longer because of the fact that there's going to be a smaller amount of bending in that light. Now, mathematically, okay, and you want to talk about, describe how the focal length and the position and size of the image. Make sure that you address what happens to the size of the image. Is it going to be bigger or is it going to be smaller? Okay, that's what you want to think through. All right? So go back and look at that diagram on that top of the page on C. See what's going to happen there. Now, let me give you a hint. as this line comes through here, let me give you a hint. Focus on that middle line. On that middle line, is that middle line going to change if you have different indexes of refraction? No. The middle line is going to stay the same. What's going to change are those top and bottom lines. Okay? So let me give you that hint. So if you shift that focal length closer, look what happens to the geometry. If you shift that focal length further out, look what happens to the geometry in terms of where those rays cross. Okay? But you're not going to change the middle line. Right? Alyssa.
Is there a set for this? Like,
Is there what?
a lab, like an online set?
The PhD.
No, I don't think so. Not where they change the index of refraction. If there is, I've never seen it. Big Mike.
No, they're not.
No.
I was drawing a ray diagram.
No, you should not get 200% error.
And there's a I did not get 200% error. I did not get 200% error. But hypothetically, I was drawing a ray diagram. You know, and it was inverted. Like if it was like in this, where it's like inverted. Do I flip it on the y and the x axis?
How? It's an arrow. How do you flip on that on the Y?
Yes.
No, but let's pretend like it's not.
What would you
No.
draw that as?
Okay. Let me give you a hint, if I may able to give you a hypothetical answer. Okay. You have drawn hypothetically a 4 as it went through a lens lab. And you might be able to go back and look at that as a reference.
So hypothetically, if I got it wrong because I didn't flip it over the x-axis, should I flip it over the x-axis?
Hey, just use a camera.
Hey, you know that purple tab? There was a question literally asking.
I think if it's inverted, it's pretty simple.
There's
to
literally
flip
a
over
question
the
that actually
x-axis.
sits on the purple line.
Oh, here's the purple.
Like at the top of the third page.
That's not what Casey said. I was gonna flip it up the x-axis, y-axis.
Hey, Big Mike.
Nathan.
Hey, Borg, how do we study for this test?
How what?
How do we study for this test?
Oh, I got some stuff for you.
Oh, okay.
That sounds
Like
wonderful.
a review?
Not like a review, but I got some.
Oh, okay.
I
Hey,
got some.
Hey,
you wanna-
can we redo the test?
You said you won't ever change the middle line. What do you mean by middle? If you move the focal
The
point
one
out,
that
it's
goes
gonna.
from here.
I go straight through the middle.
Ryan, it's called the line in the middle.
But that one's going. That's going through the focal point.
What?
Or is it going?
No.
What?
Not the first.
Okay.
It's the object and goes straight into the middle.
Literally. goes
Okay. Okay.
straight
So
through
it
the
made it look
middle.
like it was going through the focal point.
Huh?
It just looked like it was going through the focal point.
No. No, there is one that goes through the focal points
Which honestly I'll watch.
like these. That goes through those two focal points.
Yeah, that makes sense.
All right, we good? If you want to hand this in tomorrow, you can. If you're done and you want to hand it in now, that's up to you. So, stop the camera.